Swayam Prabha. Digital India. Educated India.
Okay, so let us continue with this lecture. That's last one for today. That's about material recycling and corrosion issues. And as I mentioned, that I'll focus more on aluminium, and I'll show you why that aluminium is more important. And so whenever you are recycling a material, that thing what I wrote here is important. The quality of the products versus the sustainability. If the quality of the product is too low, and you need to, the corrosion is very high, and that way if you are using that material in a component or product, and you have to replace once in a while, or you have to use very costly protective system, then it's not increase the sustainability. So sustainability will not come just with the recycling. Sustainability comes with the recycling, and recycling has to be easy on the first instance, and then recycled material has to be a certain quality so that it is comparable with that of the virgin products, and that way you don't need to use excessive money, you don't need to spend for maintaining it, and then only the recycling becomes sustainable. People are, of course, there is also a concept in the recycling called downgrading. Downgrading means as you recycle a material become more and more impure, and you use in a product which is downgraded. So you must have seen that, like for example, it is more used not in the case of metals but other things, like these paper products. You can see that the paper, whatever paper is used, it goes back and recycled. Now if the quality is bad, it's downgraded, that is coming as a face tissue and things like that. So it is that way you can downgrade and use it for different applications. And in the case of metals also is possible, and people are thinking, I'll come to that bit later, but otherwise this is important, the quality of the versus sustainability, and this is an important thing today, when especially when you are thinking the use of the aluminium. So just a little bit on aluminium, because we focus so much in our research on this recycled aluminium. We work with two things. One is understanding the recycled aluminium and corrosion issues, and how we can reduce that problem, so that people can, companies like the Hydro Aluminium, which we are collaborating, they can make a product, and still the recycled product, they can sell it and people can use it. Recycled aluminium also cause problem for the surface engineering, especially for this anodizing part. When you do the anodizing, and especially people are trying to get decorative anodizing, especially this company called Bang & Olufsen in Denmark, they make very, very high profile products. Like these fonts are not existing now because nobody uses the land font. And so these fonts are not existing, but they were making this kind of fonts, which is probably cost 60,000 rupees for one other font, like that. And but it is high profile products, like with a very nice surface finish and things like that. So they make sound systems basically, but all their products are packaged in aluminium, and which is anodized to get a good appearance, optical appearance. So there they will not accept any little bit of change in the reflection. That's not good for them, because design is their value. So if you take a Mercedes-Benz car, BMW cars, interior sound system is designed by their company, and with the all aluminium covering and things like that. So that's kind of things you can understand. So there it affects. Just to give you a glimpse of that, and as well our work with this, because I will not go into that. Recently for this Bang & Olufsen company, we also made a process for making the white anodizing. You can make with the anodizing all these colors in the past, but you cannot make the white color by anodizing. But we made a process by which they could make the white color by anodizing, and then you can use this white color as a base. They can also get this kind of pastel colors instead of these bright colors. So they are now using it for their design. But I will not go into that detail. But another important thing here is that the recycling and how that affects the appearance. So why the aluminium is most important? Because aluminium, as you know, that aluminium is a material which is very light. It is a density which is coming almost, if you look at here, the density of aluminum is, this is aluminum alloys are coming here. The density of aluminum, if you take here, and steel is here, which is coming almost 1/3 of the steel. But the density alone is not enough, because you also need the strength levels. But rather more important is the strength divided by the density, that's more important. So if you take the strength to weight ratio, and that's what I put this line slope here, and you can see that if you put as line here, it shows that all the material that is lying on this line has a similar value of this ratio. So if you look at like that, you can see that aluminum is coming here and steel is coming here. You can see that steel is below this line, which means that if you take the strength to weight ratio, aluminum is higher than steel, because if I put another line here for the steel, only this top part of steel, still the aluminum is better. If I take the top part of aluminum, it goes like this, which is much higher than steel. So that's the advantage, that's the interesting thing, that is aluminum is interesting used for different applications. So you can get a similar level of strength to weight ratio or higher level of strength weight ratio compared to that of steel, and that way if you replace the steel in all applications, you can get a lot of benefit. And that's the reason that aluminum is entering today into all kinds of products and much more into the automotive. You can see that 2011 to 2020, you can see that the amount of aluminum use has increased so much in the automotive. A big shift you can see in US, and because US there are many things that is contributing to that. One is that the petrol price is slightly increasing in US, and that means that people are looking for, also started looking for, earlier Europe the fuel cost was high, and so European people were looking for always lightweight and smaller cars, but US it was not a problem, but now the fuel price is increasing, they are also looking for better cars. And another thing is that is also with the environmental concern and things like that, there is a lot of shift. So you can see that there is a big change in this one. China is using and Europe is using, so you can see that there is a lot of increase in use of aluminum into the cars. And this is the scenario. I'll come to that, but it's also the case that it is like aluminum is, aluminum industries also want to push aluminum into the automotive industry, because they are also, aerospace always aluminum is used, and aerospace now use a bit less aluminum because of composite, and that's the reason that they want to push also this aluminum industry also want to push this aluminum into the automotive industry. Another thing is that this electrification. Electrification means, yesterday I told you the relationship between battery pack and the weight of the car. So petrol cars with a filling, one filling you can go up to 850 or 900 kilometers if you do, if your petrol tank is like 50 liters or something like that. And but with the Tesla, with the ultra modern Tesla also can give only around 400 to 450 kilometers. And in European weather with the cold, again that will come down, because you can never charge that to 100%. And amount of electricity used is very high with the heating and things like that, the mileage will come down. So if you want to increase the mileage, you can do that in two ways. One is you reduce the weight of the car automatically, that for the same 1 kilowatt or whatever, you can drive more. So that's one way. Another way you can think is that if you reduce the weight of the car, you can put more battery, and it means you can more power you can. So all the electric vehicles will be using so much of aluminum in their body, and that's what is going to happen. Now it is used, but only thing is in the premium cars it is used, but it will come to the all cars, and that's the aim. So this is so there are many designs that is going on for using this in the different things, but if you look at it, main alloys that are used is mainly 6000 series alloys, which is aluminum magnesium silicon alloys, that is 6000 series alloys, and 5000 series alloys are aluminum magnesium alloys. So these are the alloys mainly used. In the aluminum side, there are different types of alloys. Some alloys are used in the aerospace. What are the aerospace alloys, you know? 7000 series and 2000 series. Aluminum copper alloys and aluminum zinc magnesium alloys, that 7000 series alloys are used because these are the high strength, very, very high strength alloys, and with high fatigue properties and things like that. That's what used for aircraft. That's too costly for the automotive industry. Automotive industry, everything is money. In the aircraft, money is not an issue. and performance is the issue in the aircraft industry. You can increase the cost of the aircraft if you can put one more seat. That's the way it goes with the aircraft. But in the case of automotive industry, everything is money. That means that they want to reduce the cost, and that's the reason that they use aluminum, magnesium, silicon alloys, 6000 series, and all these. And there are different types of design technologies from the car point of view. For example, European industries use like this, they make these extruded products like this and join together and make this frame, and then they put the sheet on the top of this. So if you put the other sheet on the top of this, they put it and pack it, and that way they make the car. On the other hand, in the US, technology is like they don't use this but directly linking together the sheet. So take the different parts of the sheet together and link it that one, so that they don't have that much of this frame like that. So there are different technologies in relation to design, but it changes only the way the shape of the material is used. Here it is rolled sheet, here it is extruded things and like that. But otherwise, the alloys are concerned, it is like this. Now we can also see this. You see here, alloy is 6016. Surface structure not important. Pre-treatment. You see here pre-treatment. They use a zirconium and titanium conversion coating for the painting. You mentioned in the last class, right? So instead of that phosphating, in this particular case, they are using the zirconium titanium conversion coating. That's what they are using. Probably because the reason that this is only aluminum frame. You don't have the zinc here. So it's only aluminum frame. So they go for the zirconium and titanium. Again, it is a chromium-free treatment in that sense. And why they want to, now come to the recycling part, because the problem is with the aluminum is that aluminum is much more costlier than steel. So if you take the price here, you can see that aluminum is at least 3 or 4 times more costlier than steel if you take the virgin aluminum. And although if you take the galvanized steel sheet is a little bit higher than this, because this is the steel price, but when you coat that with the zinc, price will be slightly higher, but still aluminum is very costly. So the only way you can expect aluminum to coming to the every cars is by using the recycled aluminum. There is no other choice. Virgin aluminum cannot be used for any of these applications, and that will not be cost effective. So that's the reason that recycled aluminum is important. Recycled aluminum has many steps in this. It's not an easy process. Recycling is also not an easy process. You need to collect the scrap, right? You need to get material for recycling. If you don't have the material for recycling, you cannot do it. So you need to get the material for recycling. Then you need to do the scrap separation as much as possible. There may be, when you collect the scrap, there may be 6000 series alloys, 5000 series alloys, 2000 series alloys. You need to separate that. There may be steel parts. You need to separate that. So separation is another thing. And then you do the remelting. And that comes to the question of this overall product quality, which we are going to discuss, and then it comes to the overall cost as well. So then that is what determines the sustainability, all of them. But this is an important part that is determining the sustainability, for example. This is also an important thing. For example, in the Europe, it is possible to, I don't know the situation here, maybe that is here as well. In the Europe, it's possible to recycle aluminum basically because every product has to come back. So, for example, if I have an aluminum product and I cannot just throw away that product, when it is finished, I'm not using it. I need to take that product into the recycling center. There is recycling center everywhere. Probably from my house, if I drive 2 kilometers, there is a recycling center. I need to take it and put it there. That's the way it is. Similarly, if I use a soft drink can, which is made of aluminum, I need to put it into separate bins. So there are bins for polymer, bins for metal cans, and like that. So it is separated. So from the house waste, when they collect itself, is separated. And not only that, nobody will put this can into the bin because there is a thing called a payback mechanism. Payback mechanism is whenever I go to a shopping supermarket and buy a Coca-Cola or something, some can, if I buy drinks, I'll be paying, because in Denmark, the money is Danish kroner. I'll be paying 1.5 kroner extra when I buy the drink. Then once I finish it, I can go to the same supermarket or any supermarket. There is a machine. I can put this can back there and then I get back 1.5 kroner. So it's a payback mechanism by which they make sure that all the cans are returned, and that way they can do the recycling. That's very, very important. And because there are some people have the social responsibility, and they will return it irrespective of whether there is a money or not. My wife, she is a very responsible person, and everything, because there is a lot of recycling instruction rules, and she follow everything. That means that even if there is a milk can, top part is plastic, I'll tell her, you can put that everything. And she will separate that, cut it, and put that plastic in it, and this one. But everybody is not like that. I will not do that. I will think that out. Major thing I separate, but a small thing I think that's okay. Like that. So this payback mechanism is very important, because I can tell you one story. That is, in Denmark, if you take, so Denmark place is like this. So if you take the whole Denmark, there is a place here, there is another place here, and then there is a almost like a big place like this. This is Denmark. So Copenhagen is here. And so there is a sea part here, and this is Sweden. So all these places Sweden, so it's connected to Sweden like here. And this part, if you take, this is Germany. So this part is connected to Germany here. And then there is sea here. There is sea here, and there's a big bridge, and there's a bridge here to connect like that. In Denmark, energy is produced by two ways. One is by wind energy, which I mentioned yesterday. Around 40% of the electricity comes from the wind energy. Rest of the energy coming from the thermal power plants. In the thermal power plants, they want to increase efficiency. So I think Denmark is the only place you get thermal power plants give 80% efficiency. Why 80% efficiency they get? Because the fuel what they burn in the thermal power plants is the waste that is collected from the house. All the waste what they collect, because there's a very good collection system, everything is collected from the house and other places, and that's what is burned in the agricultural waste, and all these are the one burned in the power plants. And that increases the efficiency, because automatically, produce the things which is burned there, that carbon dioxide neutralized like that. And so that is one thing. Second thing is that what they also do is that when in the thermal power plants, once the energy is produced, steam is produced, turbine is running, then you get the steam is condensed after the turbine, you get the hot water. This hot water is the one which is used for heating all the houses. In winter we need heating. All the houses is heated by using this water. So that way they increase efficiency. That's another thing. So what happens is that people found that whenever, so you have thermal power plants at many places here, many places here, many places here. All the thermal power plants here which is located close to the German border, when they collect the waste and burn it in the power plants, then after burning you get a thing called bottom ash. It's ash which is coming out. This ash contains a lot of aluminium in that. Only in the southern part of Denmark, not in other places, only in the southern, basically this region. And they started wondering that why this is. And they got an idea that maybe the reason is that in the southern part of Denmark, nobody will buy beer and cola and things like that from Denmark, because Denmark is a very costly place. Germany is cheaper, so everybody will cross to Germany. In European Union, you can, everywhere you can travel. So they cross to Germany, and there are so many Germans. What they did a very nice thing, that all over this border there are many shops. So they cross to Germany and go and buy. So we say that when the cars goes from Denmark to Germany, car will go like this. When the car comes from Germany, it will be like this, because everything is filled with the beer and all those things. So when the problem is that when they drink that, they cannot return their can in Denmark, because it is bought from Germany. And those who are having social this one, maybe they take that to a recycling center. What others will do? Others will do into the bin. So when they collect the waste and then they burn it in the power plants, automatically this can is part of that. And that is what is resulting in this aluminium, in this bottom ash. So that's an example of like why this payback system is important. Those who are living in the Copenhagen will not do that, because Copenhagen to cross here, we need to pay money for this bridge. If we want to cross to Germany like this, again we have to pay money for the bridge. So it's not profitable for us to go and buy from Germany. But here they can easily cross and buy from Germany. So that's a thing that shows that it is how important. Another thing about the aluminium is that I also told, when we think about this, like you can also see that aluminum is an energy intensive material, because you can see steel production energy is somewhere here and per unit volume. So this is for unit volume. Steel production energy is somewhere here. You can see the aluminum production energy is somewhere here. The aluminum need higher energy to produce. Why aluminum need higher energy to produce? This is the energy that is spent for producing aluminum per unit volume. Why that production energy is higher for aluminum? So the aluminum production, because of saying aluminum is more active metal, you cannot produce aluminum just by heating process. Like steel. Steel, you can take the iron ore and you can heat it with carbon and produce iron. In the case of aluminum, that's not possible. Aluminum is produced by the electrolysis process. So you need to spend a lot of electricity. That's the reason that if you look at all over the world, where you see aluminum production, Denmark will not produce aluminum because Denmark electricity is costly. India produces aluminum, electricity is cheap. Australia produces a lot of aluminum because there is a lot of hydroelectric power, aluminum is cheap. Iceland is a place there is a lot of electricity and they produce aluminum. Norway produces a lot of aluminum because there is a lot of hydroelectric power. So all the places where the aluminum electricity is cheap, and that's the place you see that aluminum is produced. But still the cost is high because it is electrolysis process. That's what also you see here at the carbon dioxide footprint as well. So the steel has a carbon dioxide footprint which is very low compared to that of aluminum. All this chart, you may be wondering that is where I get this chart. All these chart because there is a program called Cambridge Engineering Selector, which is a material database software which is produced by the Cambridge University, one of the professor there, and then there is a started company. Now it has taken over by ANSYS. ANSYS, probably you are aware, that is ANSYS software. They have taken over, and this material database software allows us to plot all these charts like that, and with a lot of data. So all these shows that aluminum is an energy intensive material, just to bring back again to the point that recycling is important. When you recycle, there are many issues that comes, but I am just focusing on two issues. One is that, as I told you, these iron containing intermetallic particles. Because if you look at here, the iron solubility in the aluminum is very, very low. Very little aluminum can be there in the solid solution of aluminum. So that means that all the iron will be precipitated as these iron containing intermetallic particles. Naturally, it is a cathode for the corrosion process, and that way it can create problem. It's not just corrosion problem, it can also cause problem for other things. It's also a problem for fatigue and things like that. But we are focusing today on corrosion. That's the reason that I'm talking about corrosion. Otherwise, it also causes problem of fatigue. Another problem is that you cannot avoid trace elements of copper and zinc in the alloy. And copper and zinc is very, very sensitive element for aluminum because copper and zinc is always cause the intergranular corrosion problem. Copper and zinc can easily migrate to the grain boundary and sit there, and because of the potential difference between copper and aluminum, and then it can cause grain boundary corrosion problem. Copper create a problem, zinc create problem. But you can also think that copper and zinc together, maybe it's better. Because if you think the electrochemical series, one is noble, other one is other way, and probably is neutralized. I'll come to that. You can also see the composition of the copper here. It is less than 0.05. That means that at a level which the companies cannot almost control. So it's a very, very low level of copper what we are thinking about here for this intergranular corrosion. But we will come to that later. First, take the case of these intermetallic particles. Again, I think the best way to show in that really how it that cause problem for a product. And I took two products here. First, take this one. So this is a profile for the windows. So there are, this kind of windows are so much used in Europe because in Europe sunlight is less. So always we'll have the window on the ceiling which you can open automatically, and you get some sunlight. And if there is a lot of sunlight, there is a shade, you can close it like that. So this frame is made of aluminum here, and that is what you see here. You can see that there's a painting. That painting has corroded. You can see this blister formation here after some time. They didn't expect that. Because this product, they are selling it for a long time, they didn't have this issue. Suddenly they started getting these corrosion issues here, and then they analyze what is happening here. So then they took that cross-section and things like that, and then what we did is that we took the microstructure of that material. When we took the microstructure of the material, we were really surprised because we can see so many intermetallic particles. All this white color is iron-containing intermetallic particles, which normally we don't expect in an alloy. Then we took the cross-section, you can see that everywhere you have this corrosion, and that area you have all these intermetallic particles sitting there. Answer is very clear, because they used a recycled aluminum alloy. Earlier they were not used in the recycled aluminum alloy, they shifted to recycled aluminum alloys. All the paint system what they are using is not good enough for that, and that's the reason that it gave that problem. So then we discussed with that company, and it is clear that is their purchasing department, they are looking for always reducing the cost, and then they asked different companies whether they can supply the aluminum or not. One company told that yes, we can give you with a lower cost. The problem is that if you look at the ASTM standard for aluminum alloys, everything is in a range. So they will tell you that, for example, if you have 60 or aluminum alloy, and then they say that magnesium is say 3 to 4%. It's not may not be correct. I'm just writing something. Iron is maybe from 0.001 to 0.03%, like that. That means that anything within this range is 60-60. It's up to you to say that I want 60-60 with this level, lower level. So this they don't understand. This company won't understand. So what happened was, when they told that we want 60, company told that we will give you 60-60, but the only thing is that iron is on the other side because it's recycled aluminum. And that they supplied, and then they started getting this problem. So many products failed. So you can see that from the business point of view, how bad it was with so many of these things that failed. This is another problem. Now what happens is that they try to make this kind of products with coated, but this base material here is extruded, right? It's extruded product. And when they do the extrusion, this material is hot extrusion they do. Those material they heat up, it will become a little bit soft, and then they extrude. If you look at this intermetallic particles contains iron, right? Iron is a little bit harder than aluminum. So because of that, when you do the extrusion process, this particle will not flow in the same way as aluminum. It's like you take chapati, dough, if you take, or like that, and you can try to extrude it, you get a raw sort of thing, right? But you try to put sand in that and then try to extrude it, you will see that sand get collected around this extrusion die, basically because sand will not move like the wheat flour which mixed with water. So you will get the collections. That's the same problem that happened here. So that particle get collected, and then once in a while that get released. So on the extruded surface you get this kind of pickup, like a sand particle sitting. They didn't realize that. They did the etching process, cleaning process, conversion coating process, everything. But at the end, your metal surface is with this kind of things, with this projection. When you put the paint, here you don't have the paint because of this projection. On the flat surface, you have this projection, and there you don't have the paint because of this projection. And this part of the area is totally collected with intermetallic particles. So that's a very active material from the corrosion point of view. Suddenly what will happen is, this area corrosion goes down, and then they had the problem. Just to take just two examples, like actual product, how this recycling, which they didn't realize, and then that caused a problem. But everything, all these are due to the intermetallics. So you can see that here when we do the cross section, and clearly we can see that this intermetallic particle is all over this sitting in the corrosion area, in the interface. So there's a paint area and the metal area, and this interface you can see the corrosion product. And we also did this analysis here. You can clearly see that they did the chromium treatment. They don't know what exactly the treatment they did, but we could analyze and find out they did the chromium treatment. So you can see the chromium layer here. So even the chromium layer, I'm sure that it will not be chromium 6, because chromium 6 was banned before that. So it must be chromium 3 treatment. After the chromium 6, Then the chromium 3 treatment came, which is better than the chromium 6, and that they used, and it is still not protecting this. So it shows that even the chromium 3 is not good enough to protect the recycled aluminum surface, for example, from the corrosion when it is painted. You can see that there is another problem comes with the recycling. For example, when you have the roll sheet, so material is sometimes you want to make it like a sheet form, right? So then it is rolled. When you have the rolling process, this contains a lot of this intermetallic particle because iron impurity. This rolling process creates a lot of very high shear deformation of the surface. So this high shear deformation of the surface fracture these intermetallic particles. So when you take a roll sheet, and if you go from the top to bottom of the roll sheet, like a small thickness going from top to bottom, on the roll sheet, you will see that intermetallic particle size is changing. You have very fine intermetallics in the top and big intermetallics in the bulk. Because this is like bulk one, if you fracture this into fine particles, you get a much higher surface area than this one, this fractured particles. So this gives much higher surface area, and this one is very, very corrosive. You can see that here. So this is on the top, and this is in the bulk. So we put that in the acid, just hydrochloric acid. So yesterday, Lakshman was talking about the hydrogen evolution. So you can see the hydrogen is evolving in all these particles because all these particles are acting as cathode. You can see so many places, right? And here you have less places. So here you have more cathodes because it is fractured intermetallic particles and compared to that of the bulk. What is the problem? If you don't remove that layer and do the painting with the conversion coating and things like that, and then you get a very this filiform corrosion problem if they use it for the automotive industry, for example. So that's the issue. So that's what I'm just showing here, and so you can actually we did the electrochemical profiling. So did the electrochemical profiling from top to bottom with different depth from the surface to bulk. With the different depths, you can see that as we move from the bulk to the surface, the anodic activity is higher and higher current. And you can also see the cathodic activity is higher. Because when you do the electrochemistry, because of this microstructure, what you get there. So what people do normally, they take the aluminum alloys before they do the painting and conversion coating and everything, they do an etching process. They put it in the alkaline solution and etch at least 1 micrometer of the surface, they remove it so that they are already in the bulk. But again, people can do mistake in the companies because it depends on their knowledge, right? If 1 micrometer, they didn't remove 1 micrometer, they removed only 0.3, still they are in the region, all the products will have the problem. So it's a tricky thing to take care, that's what I'm saying. There's a solution for it, but the thing is still they can do the mistake. So we also did the experiments with the different ion contents, so such starting from 0.4 to 0.42. Clearly you can see that as the ion content is increasing, you have more intermetallic particles, electrochemically very clear the effect. You can see here that with increasing this one, your OCP is shifting towards more anodic side. It is shifting. And we can see that with a higher amount of iron, even you start getting the pitting, even at OCP. So all these fluctuations show that even at OCP you are getting the pitting, like that. And that's what also you see here, that is with increasing the iron content, your anodic activity is increasing. With the less iron, you get a passive this one, but that's disappearing with increasing iron. You also get increasing cathodic activities with increasing iron. So it's very clear the effect with a different amount of iron content. And this is a typical bracket like 0.04 to 0.42. This is a typical level of iron what you see it in the recycled aluminum alloys. These people from Australia, they have done a study where they took the aluminum iron alloys and then they did the different cooling rate. So that means that they melt the alloy and different cooling rate they did for during the casting, and then they took that microstructure and look at the corrosion behavior. Again, you can see that if the cooling is lower, so here you have a high cooling rate, Here you have a lower cooling rate. If the cooling rate is lower, you can see the corrosion rate is higher. That's what you also see here. So again, showing that basically why all these things they do, cooling rate, because when they want to make the recycled aluminum, first they will melt the alloy, cast it, then there is annealing process, all these places there is cooling steps. And they want to know that how the cooling step is affecting differently compared to that of the virgin alloy. Now coming to the little bit of the application side, you can see here that is Andres. Andres he was working with Alcan earlier. He was my collaborator, and now he is working with what is that company? I don't remember the company name now, but he's still in the aluminum area, working in US now. And Andres has done a lot of work. His PhD thesis was fully related to the effect of iron in the aluminum and how that caused a problem. And so here you can see that again what I was talking about, that is surface has can you see here? Surface has more intermetallic particles compared to the bulk. Here there is more white color compared to the bulk. So if I go from the surface to the bulk, then the number of intermetallic particles come down. And you can also see that effect here. Then he did the filiform corrosion testing. So what he did first, that is he did the just acetone degreased. So just cleaned with acetone and he painted, and then he did the filiform corrosion, you get a bigger growth. Then he did the chromating on the top of that. Chromating will reduce the filament growth. Chromating is good actually. He did the annealing process. So that means that he did a heat treatment to this. So that heat treatment created more intermetallic particles to form. So that again increased the filament length. Again he did this chromating, that brings down. Chromating is protecting it. And if you look at all these, you can see that is as you can see that. And again he did another thing. He did etching. Then you can see the filament length is coming down so much. Etching means he did a alkaline etching and removed part of the surface. So then he is only in the bulk. Then the filament length has come down again when he is painted. So you can see that clear effect of all these in this work. So this is just showing that picture, like on different case what I'm talking about here. Here you have a higher length and lower length and like that. So here you can see that is really that effect. So filament length versus annealing temperature when there is iron. You can see that as the annealing temperature is increasing, you have more and more filament length. That means that what is the reason? If there is iron content in the alloy, as you do the heat treatment at higher and higher temperature, you form more and more intermetallics. And that way you have more and more this filiform corrosion problem. That's what it shows. Here he took different alloys with different iron content, and then he is comparing. And again you can see that it is like this is, if you take the hash rolled condition, that is this one, and if you take the caustic etched, and that is this one, you can see if you compare these two, I don't want to take everything, then you can see that when you do the etching process, the filament length is coming down, right? Because etching process is removing the surface and like that. But you can also see the iron effect here, that is the one with higher iron content gives higher filament length and like that. Again the story is similar, that is as you increase iron content in the alloy, which is difficult to control during the recycling process, you get more and more problem. I take then little bit into this copper and zinc effect, which is very trace level. Now we are talking about much lower amount than iron. Very, very little, less than 0.5 weight percent, that's what we are talking. Not less than 0.5, you will see that later that we found that 0.01 weight percent of copper can give intergranular corrosion problem. So it's even that level of trace level of element is enough to give the intergranular corrosion problem. Why this is important? I think that part is more interesting to understand. That is, now the aluminium, what aluminium industries are doing, they are trying to push the aluminium into automotive industry. Do you think that steel people will sit without doing anything? Steel people are also trying to do it in the other way. You know, if you can, steel is heavier, right? That's the reason that they want to use aluminium. But if you can use the less thickness of steel, lower thickness of steel, if that's enough, you can also reduce the weight, right? So if you want to use the lower thickness of steel, what they need to do? They have to make a steel with a better mechanical properties. If you have higher strength level, and then they can use less steel, and still they get the properties what they want. So steel people are trying to make a better steel alloys. Then they are thinking that they can compete with aluminium. So now the aluminium people have another problem. That is, the steel alloy, new steel alloys are coming up, which has a higher strength level. All these steels. Now the aluminium people has to push this into that if they want to compete. And when they want to compete to that level, they need to work with this precipitation. Precipitation means now they have to do I don't know how many of you are familiar with the aging heat treatment for aluminium. Aluminium means they do the heat treatment called aging treatment to form the precipitate. And they have to do that. When they have to do that, it has to go through this aging treatment and things like that. There, this amount of the copper and amount of the zinc becomes important. So when they do the heat treatment, even with that small amount of, maybe I'll take this small amount of copper. So you can see the not 0.01, I did a mistake. 0.001 weight percent to 0.05 weight percent, you can start getting the intergranular corrosion problem. Why that intergranular corrosion problem is coming? Because as you can see that the copper is, so that's a TEM image. Copper is segregating. Copper is from the bulk, it is segregating into the grain boundary and collecting the copper at the grain boundary. So you can see that this line profile image around this grain boundary area, you can see that you get a higher copper. So that shows that copper is segregated at the grain boundary. That means that near to the grain boundary, copper is depleted. Then what is the problem? That's where the intergranular corrosion is created, right? So you have a grain boundary. So copper is sitting here, and that means that there is no copper here. So now this one is electrochemically, this one is cathodic, and this one is anodic, right? Because less copper is anodic and more copper at the grain boundary is cathodic. And that way you get the corrosion going through here, like that. That's the intergranular corrosion problem, right? So we could see that even with 0.001%, there is segregation at the grain boundary of copper. And there are more results to that. We don't want to discuss, we just to give you a brief this one. So you can get the copper film at the grain boundary, and then you have the copper depleted layer, and then that is causing the intergranular corrosion problem. So this also is given by the zinc. So if you take different alloys here, so starting from 0.001 copper to 0.05 on this side, and 0.001 to 0.08 zinc on this side, different alloys. If you take, so even with a low element amount of copper, you get higher and higher intergranular corrosion problem. If you get zinc, zinc also will do the same thing, going in the other direction. But only difference is that when the zinc comes to the grain boundary is anodic and this region is cathodic. It changes. That's the only difference. But otherwise, zinc also will segregate and then give the grain boundary corrosion problem. Since I mentioned about copper, this is cathodic and this is anodic. In the case of zinc, this is anodic and this is cathodic. That brings us probably a solution, right? You compensate with copper and zinc. So you can see that when you try to compensate with copper and zinc, yes, you can. So if you look at almost in the diagonal region here, where you have copper and zinc together, you get less intergranular corrosion problem compared to going in this direction or in this direction. Because copper and zinc is balancing out at the grain boundary. So that means that grain boundary engineering sort of thing, so where you are making the electrochemical potential almost equal, And this might be a good solution for them, so that they know that there is a little bit of copper, probably add a little bit of zinc to compensate that. So, but electrochemically, this is a very nice thing to see. Such a narrow region, very, it's a micro level. And you can see that how we can tailor an alloy. How we can tailor an alloy, how we can tailor the grain boundary, and that way you can reduce the integral corrosion problem. That's what it shows. This iron-containing intermetallic particle also cause problem for the surface modification, anodizing. So you can see here that is, I'll come back to that, but I just want to show first this. Why it causes a problem? Because what happens is when you do the anodizing, you are converting part of the metal surfaces to aluminum oxide, right? That's what you do anodizing. You use an electrochemical process and that way convert the part of the surface. So this is a metal part. Part of the, initially the metal part was almost up to here. Part of the metal part you converted into aluminum oxide. Now what is the problem when you have intermetallic particles in the microstructure? This intermetallic particle composition is different from the aluminum, right? This intermetallic particle contains a lot of iron. So that means that when the anodizing occurs, this will not get anodized as fast as the aluminum. So result of that one is when the anodizing occurs, part of these particles will be remaining in the anodized layer as metallic particles. So at the end what you get is you get an anodized layer with these metallic particles which is inside. What's the problem with that? The problem with that is normally this anodized layer is transparent. Like you can see your Apple laptops. If you have Apple laptops is anodized. That's an anodized aluminum. You see the aluminum surface through that anodized layer because anodized layer is transparent. So if you start with a mirror finish aluminum, and you will see the mirror finish surface because anodized layer is transparent. But when you have this particle inside, it will look like a little bit of darkish color. That's because when the light is going inside, metal is a very good absorber of light. All these metal particles will get absorb a little bit of light. So that means some intensity of light is going in, less intensity is coming down. So the surface look more dark. This is what happens. And this is a problem with this one. So when you are looking for a anodized surface for high quality applications where the appearance is important. If it is only for corrosion protection, it doesn't matter. But appearance is important, and then this creates problem. Like this kind of thing, they want to have a mirror finish condition, and in that case, that creates problem. There was a big issue in Denmark few years back because this is the opera house in Denmark, in Copenhagen. This opera house was there. We have a old opera house, and that's really old, and probably more than 200 years old. And that's the reason that they built this new opera house. And so when they built it, they want to make all this top part made of anodized aluminum. So when they made it with anodized aluminum, they expected that the anodized aluminum will reflect more like this one. But after the anodizing, they found that some part is reflecting, some part is having a dark color. Then it was not the designer's expectation didn't come the way they want, and it was a big thing, right? That one. So a lot of money is spent on that. And they came to DTU and asked why this is happening. And immediately we told them that it must be due to because you used the recycled aluminum. That's exactly the case. So it was a court case. It was a court case. For those who built this, they are saying that it is a problem of the people who did the anodizing. Anodizing people are saying it's not our problem, it is a problem with the aluminum suppliers. Aluminum suppliers are saying that it's not our problem because you asked us certain type of aluminum, we gave you that. You understand? That way, no, it's a very difficult case to solve. And that's the reason that at the end, the court judgment was like responsibility is with those who bought the aluminum. Because the aluminum companies, they supplied according to the specification. Anodized people, they did whatever is required. The people who purchased aluminum, they should have thought that this recycled aluminum, they shouldn't buy. So that, and it was like that. So, but whatever it is, it was a very big court case, exactly because the same problem, they use recycled alloys, and then they get this problem because recycled aluminum causes problem because this intermetallic particle get into the anodized layer, and that affects the reflection, for example. So here you get a good reflection. Here all these particles absorb a little bit of the light, and that way you will not get a good reflection, and then means the surface will look more dark. Again, we are working with this company, this Bang & Olufsen, this company. We had a PhD program, and we were looking into try to solve this problem. So normally people do the DC anodizing. I'll not go into detail. I'll stop now. And people do the DC anodizing, direct voltage anodizing. You apply 10 volts, you have a direct current, do the anodizing. So we thought that maybe the pulse anodizing will solve the problem. The pulse anodizing means you give a positive pulse, you anodize, then you drop the voltage. So for a period, no anodizing, then you anodize, then you non-anodizing. Why we do that? Because the problem is that as the anodized layer is coming down, so you have an anodizing solution. As the anodization occurs, the solution should get enough time to interact with these particles for this particle to get anodized more. So in order to give that time, we thought that when we do this pulsing and no pulsing, so that period you can have this electrolyte interacting more with the particles, and that way you can get better anodizing. I'm putting in a simple bar. It's not that simple, but in a simple way, you get more time for anodizing. That way it's better. So you can see that we did the experiment. So you can see here, like here it shows the reflected image quality. Like when you look at the surface, how much reflection is there, the image quality, that's what is specified here. You can see that with a recycled alloy, DC anodizing gives around 65%, but if you do the high frequency anodizing with the pulsing, so this is 1 kilohertz and 5 kilohertz pulsing, you can go up to around 80% reflection quality. So you increase the reflected image quality. Always compare the DC. If you do the different pulsing, in general you increase the reflected image quality, for example. You can also see that in probably here. So here as well, I think which one is better to show? Yeah, this is enough. So this is the reflection. You can see that. So you can see the DC anodizing. After that, you get a kind of a diffuse one. But here you can see that a particular angle. When you look at it, you get a very nice higher reflection here as well. So it improves. It improves the quality, but whether that improves to the satisfaction of that company, that is different. Because that company is looking for probably getting a reflectivity more than 90%, for example. So that's different, but it improves. And still we are working on this one. So, but overall it shows that it is also a cost problem for the anodizing. And so that's another issue. I think that with that I want to summarize. That is, you must have got some idea about where we are on the aluminum recycling and what are the issues. But this effort will really continue because aluminum has to be the material for the future. Composite as well, but you have a problem. There is a problem with the composite for many applications because composite is costly. One thing, polymer metals composites. Second thing is that if you go and ask automotive manufacturers to use composite in their products, nobody will use because they have to change the manufacturing line. You cannot use the same process line where they make the metal cars, alloy metallic cars for the composite. When the aircraft industry changed to composite, they changed totally their production line, which none of the car companies can afford that, especially with the competition today in the market. So nobody will take composite. So the only replacement for the steel is aluminum, which can be cost effective. So it's a good research area to work. I think there is, there is Indian aluminum company, I think. Indian aluminum company has taken over one of the big Western aluminum company called Novelis. So there is a lot of drive for the aluminum in the Indian scenario as well. And because this Novelis is part of the So I think the thinking that they took the Novalis takeover is thinking that with the Novalis technology, they could produce the aluminum in India. That way they can push the aluminum into the world market cheaper. So this is the whole idea. So that drive also they had to think about the recycling problem.